I adjusted the volume here, so if I come out a little bit louder, I'm sorry. And I'll continue to play with it as I work my way through things here. I also try to enunciate. Let's review a little bit our exponential function in its general form. And I will make a graphical representation of it as we talk about these properties for it. Function crosses the y-axis. Well, that's going to be when x is 0, and anything to the 0 power is 1. So that's the point. 0 for x, 1 for y. It rises rather quickly. And if we get negative values of x, it asymptotically approaches 0, but never gets to 0. And so this is going to let us talk about our properties, and this graphical representation for it can help us understand these properties. And this is kind of where I left off the in-class lecture. So one, this function, the domain, where all acceptable x values, well, x is all real numbers, and we think of that as being from negative infinity to positive infinity. The range, the output, it can't get to 0, so we're going to put a open parenthesis there, and it races off towards infinity. So all exponentials have this when they're in this base form. No matter what the base is, if the form is this, we know this is the range of the domain. And for all of them, when f is 0, the function equals 1. Again, this form. We're going to mutate this form shortly. We just want to talk about the form in itself. And I made a point, if the base is greater than 1, this grows. And if the base is less than 1, but greater than 0, this decays. And we'll do some of this in the homework problems. You should have already started seeing them. So for the blue one here, we'll say b is greater than 1. And what I'll do is I'll make a purple one here for b less than 1. Again, it doesn't cross or touch the x-axis. This is just me drawing. And so it comes in from negative infinity or positive infinity, gets less, hits 1 when x equals 0, and gets closer and closer to 0, but never quite there. And so b to the x with b trapped between 1 and 0. Now, I made a point, and this is worth noting because we'll use this, that if b is between 0 and 1, it's fractional. And so what I could say is I could really rewrite this using my laws of exponents. We'll say b is some fractional value. So then when I put that into f of x equals 1 over a to the x, that's the same as 1 over ax. But we know that a power in the denominator can be written as a to the negative x. And once we get past the introductory chapters, we will tend to look at the sign in front of x as determining if it grows and decays. And we'll keep our bases with a set number of bases that are greater than 1. But this is still true. And there are some people that when they work with half-lives or things that cut in half, they'll use 1/2 in here because it's easy to set up the model. We'll go both ways on that. And then let's see, what other properties did we have here? pad for a second. Here we go. F of x equals bx is 1 to 1. Every x value has one y value, and that y value points back to one x value. There's no duplications of numbers in here. And it's asymptotic to y equals 0, which is the x-axis. It approaches the x-axis, but never touches it. It's closer and closer. As we get closer to infinity, it's getting closer to 0, but it never gets there. And so these are the properties we're going to look at. Well, what we can do, though, is we can transform these. Transformations can happen. So I'm going to do a big set of axes here, and I'm going to do my transformations on this. So let me do in blue. Again, not touching the x-axis. And so we'll make this f of x is some base to the x power. And remember, this point is 0, 1. Now, types of transformations I can do. Well, I can shift this vertically. So a vertical shift is I add to the output. I add some c value. And let me change the color here to do my vertical shift. So I'll do that in purple. So f of x, I'm going to shift up some c value. Now we really only have two things visually in this general form that we can do, and this can help us draw the whole graph. I can move up c from this point, and let me get that, and this moves up c, right? The x-axis moves up c. And so when I have a shift in c, the asymptote increases by c, and this point increases by c, and my new function shoots off towards infinity here and is asymptotic to whatever the value of c was. Now, c could be a negative number, and that was, so a positive c is up and a negative c is down. And the same thing would happen here. We would shift it down, and that's a vertical shift. We can have a horizontal shift. Where I add something to x. So let's do a horizontal shift in red. So f of x equals b of x, and I'll use plus a. I'm going to have to think a second for this. I know when whatever is in this function equals 0. So a positive a plus a shifts left. Right? And so I'm going to move this back a distance of a. And so it shoots off towards infinity from here, but still goes down and asymptotically. And it's separated from this by a distance of a everywhere around. And so a horizontal shift adding to x. Well, why would that happen, right? This would be negative a. Well, look what happens if I put negative a in for x. Negative a plus a is 0. So at this point, I get the same value I would have had here. Horizontal shifts always bugged me when I was doing graphs because it goes in the opposite direction, I think. Adding here moves to the left. And if a is negative, it moves to the right. But notice how I still use the two things I know for sure about my function to regraph it. This point where it's 1, I shift that to the left if a is positive, and then I shift everywhere along the graph down, but it's still asymptotic. And then the other thing we can do is we can stretch or shrink it. And I'll use my last color here, and we'll get lots of things. So a stretch or shrinking of the graph. And that's if I have f of x equals, let's see, I have a, b, and c, so I guess I'll put a big D in front of it, and I'll make it big, e to the x. I'm going to multiply it by some number. And what that does is that multiplies this by a number. So it makes this really large, and it makes every point increase more rapidly. And as I get smaller, decrease more rapidly. So it makes it much steeper when d is greater than 1. It makes it very, very steeper, and this point jumps up. If d is less than 1, and I'll do that in orange, it's down here, it gets smaller, and it doesn't rise as quickly. And it doesn't decrease as quickly. And these are the three types of shifts we can do. And we can combine them all. Again, use your order of operations. Do your multiplications first. Do your do your horizontal shifts first. Take your main graph, move it over. Then do your multiplication, move this point up and down. And then do your vertical shifts. And you get the new graph out of it. And so we can take this base form and we can change things to it. For us, what we use for modeling, well, this ends up being our starting number, right? This is the value we start with. And this, well, if it's asymptotic to 0, and that's the lowest value it can be, this becomes our minimum number. All right? If I shift up with C, my graph will never get below what C is. And then in the A part is kind of the start. And we'll talk about a lot of this in time. It's the starting place, or the start time. We move forward or backwards from where we're starting for this. So when we go to make things in reality that resemble these graphs, these are useful for having the function do what we want it to do, what part of reality we want to match, being the starting number of things, the starting place, and the minimum number that we can get into.